Okay, we're back. So next we're going to talk about another trick that exploits spatial redundancy in an image. This is section 7.7, transform coding. What transform coding does is it exploits spatial redundancy by using a series expansion of the image. So that'd be like, imagine a Fourier series. We're going to look at other specific series, but you can use that to imagine the idea. A series expansion of the image to represent the image with as few terms of the series as possible. And we actually represent the image by the coefficients of the terms. So that'd be like, in the case of a Fourier expansion, it would be the Fourier coefficients. Now, before I launch into the first approach, let me jump way ahead to see how this works in an example. I'm going to upload this, so you don't need to write this down. So let's say that we have an image of the letter A, and we want to compress this image to store it in a way that's as compact as possible. Now, this letter A has, I think it's probably 8 by 8 pixels. And we're going to see this size of image as we move into the method of JPEG compression. What JPEG does is it breaks the image into little 8 by 8 squares and then tackles them one at a time, compresses them one at a time. So let's see how we might compress a little image of the letter A. Now, if we think about it, an image of the letter A is really a list of pixel values. And so if we use our vector notation for images, we could write it like this. It's a list of 64 pixel values, 8 times 8 pixels. Now, another way to write this is as follows. We don't usually think of it this way, but when we talk about a vector, what we're really saying is that the vector is described in relation to the standard basis. That's our usual vectors, basis vectors that point in orthogonal directions, where each one is a vector that's like 1, in this case 1, 0, 0. There's a basis vector here that's 0, 1, 0, and a basis in this direction that's 0, 0, 1. Now we have 64 directions. I can't draw them all, so I'm trying a simplified 3D example where you only have 3 pixels. But when we say a three-dimensional vector x, such as x equals 4, 3, 7, what we really mean is it's 4 of this vector, the 1, 0, 0 vector, 3 of that one, 7 of that one, right? And so when if I were to read you this little image over the phone, I would read you the numbers 4, 3, 7, and you would know that that means to do this summation in a sense. You don't usually think of it that way, but that's what you're doing. And it's in terms of these basis vectors. Now, this is a very not efficient way of communicating an image, because in an image, typically, a lot of the pixels are sort of similar to each other, particularly if it's a little 8x8 image. Now, I've picked a letter A is actually somewhat challenging. I should have maybe picked a little image patch that's more uniform, which would probably be more representative, but that's okay. But what you see, the reason that this is so inefficient, I think you can see right away, is, let's say I only read you the first number, the first pixel value, 4. Well, in an image, what that would mean is, let's say this is like a corner of the image. That would mean put the number 4 here. And now if I stop reading, all you know about the image is the pixel in the corner. So, and the reason is that I've only told you the value that to multiply this first basis vector. The first basis vector being 1, 0, 0. So what you've done here is you've taken the 4 times the 1, and you got a 4, and then all you know is the rest are zeros. You think the rest are zeros. Okay? So if I stop too soon, if I only tell you one value, you don't even have an image. You just have one pixel. So let's consider a different basis, a different set of vectors. And remember, from superposition, a basis expansion is simply a recipe for making up a function, or a vector in this case. So let's now imagine a specific type of transform, which we'll come back to later, called a discrete cosine transform. It's a Fourier-like decomposition that uses cosine functions. So what's shown in this top row, and then in this third row, and then the fifth row and the seventh row, are various cosine functions. This is a cosine function that's essentially DC. It's got it's got a 0 frequency. Okay, so no fluctuation at all. This is a very low frequency in the horizontal direction, low frequency in the vertical direction. This is a little higher frequency vertically. This is got some frequency in both directions, and so on. And as we move up this list, these are higher and higher frequency cosines. Okay, so now, just as we did here, where we would say, okay, I'm going to read you a coefficient of a basis vector, instead of reading you a basis vector which has simply got one 1 in it and all zeros otherwise, I'm going to read you a coefficient of one of these more complicated guys. So what I'm doing here in the second row and the fourth row and this row and the last row is I'm going to cumulatively add up terms in this Fourier type series and see what happens. So after I read you the first one, the scale here is misleading. It just looks like it's black, but actually what's happening is here is there's some uniform value that I'm saying. So if I tell you that the DC value of this A image is, let's say, 100, then you would put 100 in every pixel here. And so now right off the bat, you have at least a whole little image. It has 100 in every pixel, where in this regular way of describing an image, if I only tell you the first value, you only know what to put in one pixel, not all the pixels. Well, as I start reading you coefficients and you weighting those against these basis functions, so these are, I'm sorry, I shouldn't have pointed this. This is the standard basis. That refers to this example here. Now I'm instead having these cosine function bases, but the form of the equation is the same. That's why I was pointing here. So here we have, we're taking the necessary coefficient multiplied by one of these guys and then summed up to n. So as I increase the number of terms, what you see happening is it starts to look like an image right away. It doesn't look much like an A yet here, but it's coming clearer. Now it's almost starting to be recognizable. And as I move along, it's getting clearer and clearer. And let's say by here or so, it's clearly an A. And then the rest of this is just making it look even nicer. Now this is one of the biggest ingredients of the JPEG algorithm. Excuse me just a moment, I'm having a problem with my equipment here. Okay, so remember I showed you in class a picture of a man climbing on a mountain, doing mountain climbing, and you saw little blocks, little square regions of the image that looked a bit messed up. These are those little square regions, and what you're seeing in these examples are what it means to be messed up. It means we didn't communicate all 64 coefficients that you would need to exactly describe it. Remember, to exactly describe a vector in a certain number of dimensions, we have to have as many basis vectors as there are dimensions. But if we have fewer, it's not bad. It still looks like an image. Okay, so that's the idea here. Now I've jumped ahead to the actual idea, but I want to dive more into the theory of it and teach you a technique that's very important in image processing, and which is really the foundation of that approach I just showed you. So this is more about the transform coding, but what I'm going to describe to you, maybe I should write this, is sorry, I'm trying to find the section number this would refer to. Okay, well, I've misplaced it on my desk. Oh, this would be 7.7. Here we go. There we go. 7.7.1. We're going to learn about the Karhunen-Loew transform. In statistics, this is called principal component analysis. Now, some of you will have already taken ECE 566 pattern recognition or some other similar type of course, in which case you can pretty well tune out what I'm about to describe. But for those who haven't studied that before, let's go ahead and explain the idea. So what we're going to see here is, how it is that transform coding, this idea of using a series expansion to represent a vector, can lead to a compact representation. These slides are from a talk that I gave to a somewhat less technical audience, so don't be put off by the fact that I'm explaining what a vector is. You know what a vector is. but let's at least orient ourselves. So remember, we're thinking of our images as being points in a n-dimensional vector space. Now we're going to be mainly focused in the imaging here on 64 dimensions because we're going to use these little 8 by 8 windows in the image, little 8 by 8 blocks. But for the examples I'm going to show in this illustration, like I always do, we're just going to have 2 dimensions just to make it simple. So in 2 dimensions, this point would represent one complete image, the 2 pixel values of one little 2 pixel image. But I'm going to describe it, instead of using images, using maybe a little bit more familiar kind of statistical example to motivate it. So what I want to get across here is how it is that a series expansion can help reduce redundancy or help you communicate effectively by exploiting redundancy. So in this example, I'm considering a situation where we would like to communicate 2 numbers. So for imaging, these would be pixel values, but for our little example, the values I want to communicate are height and weight of individual people. So now, instead of images, each example here, each dot represents a person. So here's a person who's very short and who weighs a lot less than most other people. Okay. Now, to get this into the framework of what we're about to do, what we're first going to do is a step here called mean correction or centering. We'll explain the relevance of that later on, but for now, what we're going to do is this. We're going to take away from each person's height and weight the average height and weight of all the people. And that way, we're going to get new variables. So instead of height here, we're going to get the person's height minus the average person's height. So if a person has 0 on this scale, that means they're average. Okay. So now all these points are centered at the origin of this diagram. That simply simplifies the math for us later on, as we'll see. Now this was originally a PowerPoint, so this should have been animated, but well, I guess I can sort of do it this way. All right, so let's suppose we were considering this process of communicating from one person to another, these 2 numbers, height and weight. So let's say that the first thing I want to communicate is the weight. Now I made this example quite a long time ago. Let's suppose a specific person has a weight of 24 pounds. That's sort of like 10 kilograms. And the question is, what is this person's height? Can you guess? Well, clearly this person is very short because this is a very small weight. Okay, and this was my daughter a long time ago when she was little. Okay, so this is relating to this idea of redundancy. Height and weight are not independent numbers. One tells you information about the other. If you have the weight, you could guess the height to a certain extent. If you know the height, you can guess the weight, because a very short person will tend to be lighter and a very tall person will tend to be heavier. And so, similar to what we did in that predictive coding that we described earlier, the linear prediction stuff, the fact that we can predict one from the other means we could we should be able somehow to compress this. Okay. So I asked this question, can you guess the person's height? And the answer was that we guessed that the person was short, and we see the answer is yes, this person is short. So this is like a little less than a meter tall. Okay. So you can ask yourself, after we have learned this piece of information, what did we learn from this piece of information? And the answer is not much. The data were very redundant. We already pretty well guessed the person is very small. But this second fact does tell us something about this person. It tells us how tall the person is for someone of that weight. In other words, is the person, obviously this is a child, but then the height compared to the weight would tell us, is this child kind of fat or kind of skinny for a child, right? But the main aspect of them, the overall size, was already captured pretty well by the first piece of information. So what caused this redundancy? Well, mathematically, it's that height and weight are random numbers that are highly correlated. And what that means really is if you draw examples, like I've done here for various people, correlated means that they tend to distribute themselves along a line. As you see, most of the values are pretty close to a sort of a diagonal line here. Now let's imagine example of data that are uncorrelated and which would not be compressible. So let's suppose that I choose a random person and ask them their shoe size, and that's one variable. And then the other variable is the price of tea in China in some market on a given day. Well, obviously, one has absolutely nothing to do with the other. If I choose a random person and their shoe size, it tells me nothing about the price of tea in China. And so if I want to know these two numbers, you simply have to tell them both to me. I can't guess one from the other. There's no redundancy, and therefore I can't compress in any way at all. So how is it that we can actually utilize this observation to do some kind of compression? The answer is we use this method called principal component analysis, or KL transform. Don't be confused here. These are just two different names for exactly the same thing. In the world of statistics, where this was invented, I believe it was first invented, it's called principal component analysis. In electrical engineering, we derive the name from a physics term, which is the Karhunen-Loew transform, but they really mean the same thing. Well, here's what this method does in essence. I'm oversimplifying here, but I think it'll get the point across. What we do is we fit an ellipse to this cluster of points. Now that's a crude way of saying it. What we're really doing is we're assuming that the two random variables, this horizontal one and this vertical one, are drawn from a two-dimensional Gaussian distribution. We're not going to get much into the details of that. But in a two-dimensional Gaussian distribution, the example points tend to fall in a roughly ellipse-shaped grouping. Okay? If we can determine this ellipse, which way it's tilted, and you see this one is tilted along the diagonal, then we can find its major and minor axes. Once we find the major and minor axes, we can rotate the coordinates that we use to describe each point to be along those axes. And once we do that, we'll find that we have a good way of compressing. Now, try to relate this back to what we were saying earlier with respect to these diagrams, where we were talking about vector spaces and the coefficients in a certain basis. These axes here are replacing the ordinary kind of, in physics class you would have called these like I, J, and K, right? You replace the ordinary standard basis vectors with basis vectors that are now pointing at these angles. Okay, so they're still orthogonal to each other, but they're rotated compared to our normal representation. Well, once we rotate the diagram, so there's the diagram from the previous page, and this diagram is simply turning the picture so that this diagonal axis is now aligned left-right, and this diagonal axis is now our up-down axis. We see that all the people with their heights and weights as compared to the mean at 0 lie along this horizontal line, roughly speaking. Well, we can interpret what this means as follows. What it means is, well, let's come back to this diagram first. If you are one of these points, and if you are, let's say this one, to the right of the vertical axis, it means that your height is above average. It's greater than the mean. That means you're a tall person. If your weight is above the horizontal axis, which this person is, it means you are heavier than the average person. This person here is this same as this person here when we rotate the diagram. So the way you would interpret this is that essentially this person is much taller and much heavier than the average person. So we might simply, in a crude way, just call this person big. This person is just generally large. Somebody down here is both short and doesn't weigh very much. That's this person here. So you would just call this person small, and maybe that's a little child, and maybe that's a basketball player or something. Okay, so you can now give an interpretation to this axis. This horizontal axis is really talking about the person's size, the overall size. So when we used a prediction to guess my daughter's height from her weight, we simply used the fact that we were recognizing that someone that short has a very small size. Or sorry, maybe it was weight. I don't remember which number I gave first. It was weight. I first said that she's very light, and from that you guessed that she's also very short, and both reflect a small size. Now, what does this other vertical axis mean to us? Well, it means that if you're above this horizontal axis, it essentially means that for a person of a certain size, you're heavier than the average person. So that's maybe easier to see over here. So let's take this person. This person has a size that's up to this value, but you can see that for that size, this person has a weight that's even higher than that. So that person is overweight. So above the horizontal is overweight, and below are skinny. But if we simply want to capture the main features of a person, We can do it very effectively by just saying this first size axis, because really most of the variation is happening here, and the up-down is a much smaller thing, not as big a deal. Now, how can that be used for compression? Well, here is how we would do it. What we would do is, the standard way, the obvious way to report, transmit a person's height and weight would just be to tell you the two numbers. Here's the height, here's the weight. But once we recognize that in this rotated coordinate system, most people are lying near this horizontal axis, we can save communication by only transmitting the horizontal component. So here in this coordinate system, here's a person, the circled person. It lies here. If I were to tell you that this person has simply a horizontal value of x1 prime, but I don't tell you the vertical, then the best you can do is assume that the person is this far to the right, and then if I don't tell you how far up they are, you just have to assume they're sitting there. But as you can see, that's getting you very close to where they really are. And if I don't tell you the second vertical coordinate, you won't be that wrong. By contrast, if I would tell you they are up this much, but I don't tell you how much to the right to go, and you just think they reside there, you'd be way off. Okay? So the point is, because they lie so close to a line, we can describe them with really just one dimension. They're almost one-dimensional. In fact, if the height and weight were perfectly correlated, meaning that all the points lie exactly on this horizontal axis, we'd only need to tell the horizontal coordinate, not the vertical one. So we could save half the communications, half the file sizes in compression terms by simply leaving out the vertical coordinate. And so the question is, why was throwing away the horizontal, this is called PC, I'm sorry, throwing away the vertical, it's called PC2. PC1 is the horizontal. Why was throwing away that direction better than throwing away this direction? Well, it's because all the variation, not all, but a much greater amount of the variation exists left to right than up and down. People were so close to this line that just telling that coordinate gets you very close to explaining them. And why is this rotated coordinate system, called the PC space, principal component space, better, more compact than the original space? It's because in the original diagram, there was a great deal of variability up and down. You see people are ranging a lot in their weights. And they were also varying a lot in their heights. And so you couldn't just leave out one of those two numbers and still give an accurate picture. But here, once we've rotated, they're all very close to this line, and therefore we can leave out the vertical coordinate and not lose a whole lot. So this is an important concept in compression. This idea is called variance decomposition. What this refers to is how the variation in the two directions is composed. Variance, remember, is the square of the standard deviation of a random number. And I'm sorry, I'm going back and forth. We saw that the heights, the heights had a certain variation from here to here, and the weights had a certain variation, which looks to be about the same. And indeed, in this example, when you measure the variances of the points, the height and weight have the same variance to begin with, 34. If we add these two, we see that the total variance in the data is 68. Now, we describe this using a concept called the percent of variance accounted for. What this means is that of the total of 68, half was due to the height and half was due to the weight. So we have 50%, 50%. Gives us our full 100%. In the new coordinates, I'm sorry to keep switching, but in the new coordinates, you see there's even more variability here. They're going all the way from one end to another, but very little variability up and down. So now the variability, which was 34 before, is 64 along that horizontal direction, and only 4 up and down, for a total of 68. So the total remains the same, but instead of being divided 50-50 between the two numbers, it's 94% in one, 6% in the other. And we draw this in a diagram called an eigenspectrum for reasons I'll explain later, where you simply plot, this is 94%, is the first one, and the second one is 6%. That's just a graph of these two numbers. Normally we would have, instead of two variables, like height and weight to begin with, we may have something like pixels where there are many, many, and instead of having a simple graph with 2 points, we'd have a graph with as many points here as there are pixels. Now, what do these axes mean? These new basis vectors. Well, again, coming back to the diagram, the first direction, this horizontal one here, which is diagonal in the original diagram, is roughly, well, in this case, it's exactly in the 1, 1 direction. So this is going up as fast as it's going to the right. So this is pointing in the 1, 1 direction. Now, if we want to normalize our axes so that they're unit vectors, which is what you normally do when you're making a series expansion or basis representation, you would have to divide by root 2 to make this be a unit vector. But it's pointing in the 1, 1 direction. The perpendicular one, the one that was sort of the secondary direction that represented overweight versus skinny, that was the perpendicular -1, 1 direction, and again normalized. Okay, so what we're saying is that if we want to capture a person's height and weight very compactly, we could simply communicate their coordinate along this direction, which is the same as here in this rotated version of the same diagram. So if we want to describe this person, we would simply read off the value here, be about like 16. We would just tell you that number, and describe them with just the one number. And that number is, remember, to find a coordinate and a basis, you do the dot product between the value, the vector, and the basis vector. So the dot product between the height-weight vector and 1, 1 is simply height plus weight. You multiply height times 1 plus weight times 1. So that first coefficient, called PC1, is really just the height plus the weight divided by root 2. So you can think of it as being, along the lines of like an average. So it's the average of your height and weight, which is sort of like, it's can be viewed as telling you something generally about their overall size. And then the perpendicular one, the one that we think we can just throw away if we want to compress, but we would have a little bit of error, but not too bad. That one's basis vector is minus 1, 1. If we dot product that with height and weight, we'd have minus the height plus the weight. So you see the difference between weight and height is this one. And the difference between weight and height is a measure of being fat or skinny, right? If you're fat, it means that compared, for a given height, your weight is large. And so the difference is a way of measuring that. Now, I thought that because height and weight are examples that we can relate to easily, we would use those instead of pixels. But we could have used pixels instead. We could have said, okay, instead of height and weight, we want to communicate the values of two neighboring pixels. If they had similar relationships to our examples of our people, that our pixels tended to, if we would have pairs of pixels, 2 pixels, they would tend to represent points, be represented by points sort of scattered like this, so that it was the same math problem. The way to interpret it is that we would be saying that our basis vectors, like 1, 1, can be thought of as little pictures, where 1, 1 are the two values of the pixels in the little picture. So that's our basis vector. Our second basis vector is minus 1, 1. That's this, minus 1, 1. So dark, light. All right? And that relates back to sort of qualitatively to where we began. You see, here's one that's a uniform basis vector. And then here's a basis vector which is showing sort of the difference between the right and left sides of a little picture. Just like that. Okay. So if we would measure 2 pixels by doing the dot product, where we'd have 1 over root 2 here, 1 over root 2, like that, we would take the two, we would represent them with one coefficient, which is simply the sum of the two values of the pixels divided by root 2, and use that to communicate 2 pixels with one number. And that's where the compression comes in. Now we know from this diagram that only giving the one number and not the horizontal axis number and not the vertical number causes an error. It's not perfect, but it's close. And so that's the essence of the technique. Now, let's talk a little bit about an illustration of how this relates to faces and facial recognition. Suppose we wanted to represent images of faces very compactly. And let's say these images have 1,000,000 pixels in them. If I were to try to represent them in the ordinary way by pixels, in order to transmit to you the values of this image, I would have to read you 1,000,000 pixel values starting in the corner. I'd say 100, 109, 207, and so on, until I got all the way down to the bottom. And as you can imagine, that's not a very efficient method, because if I would stop halfway through, you'd have half of an image. So a different approach is to develop basis vectors. So now, just as we had people with height and weight, now we have people, but instead of 2 numbers to describe each person, height and weight, we now have 1,000,000. There are 1,000,000 pixel values. We would be able to draw them in the same types of diagrams as here, except they would have 1,000,000 dimensions to the diagram. But it could be that, again, there are some directions in that vector space where their points tend to collect together. Well, indeed, if you do that with pictures of faces, here's what happens. This is the first component. This is really a 1,000,000-dimensional vector that's similar to, plays the same role as this vector. It's the main one that cuts through most people. So these are all, in this data set, these are all women. And so this first basis vector already looks like a woman. And if I would simply tell you one number, let's say 1, I could say, I want to construct this person. I take one of this face. I'm sorry, let me back up. So let's say that I want to do a basis expansion. So here are, so I want to describe each person as a sum of basis vectors with these coordinates. Here's my series. This is just like what we did a second ago. Now, in this example, this is the first basis vector. This one's the second. This is the third. This is the fourth. Okay? And each of these people is one example of this image X. These are random examples. So these are like the points in those plots that I was making. So in order to represent one of these people, using this approach, I can describe this person by applying coefficients to each of these functions and then summing. So a recipe for making this person might be use 1 of that, use 0.3 of that, use minus 0.4 of that, and so on. And you can see that after just a few of these, it may very well look quite like a person. Whereas if I only tell you the first 4 pixel values in our normal way, all you would know is the first 4 pixels in the corner of the image, and you'd have nothing like a face yet. So this is an extremely effective method of compression. So I'm going to stop the video there, and we'll pick up later on.